Okay, continuing the discussion uh, for building transistors using diodes and BJTs. The next family of gates that we will be looking at is this resistor transistor logic, abbreviated as RTL inverter, RTL circuits, and we'll look at the inverter. And it is very critical to understand that this circuit consists of the following. Um, it is, I know that in this side we are showing the circuit, but I'm going to draw it here one more time for you so that you understand the main component. And obviously, the main component is our BJT device, okay? And the base here is connected to the base of the BJT device connected to a resistor called RB. The collector is connected to a resistor called RC. The resistor RC is connected to the power supply VCC, typically 5 volt, and the RB is connected to the input. Okay, so this is VN. Okay, and plus minus. Okay, and we have this is here the emitter, which is connected to ground. Okay, obviously this is our VBE, right? Pay attention always in the BJT device that the VBE controls the operation of the device. If VBE less than 0.7, then we are in cutoff. All right, so if VBE, as we have indicated earlier, less than 0.7, when we are in the cutoff region. If VBE equal 0.7, then we are in forward active. Okay, and if VBE equals 0.8, of course here volt, then we are in the saturation region. Okay, all right. So with that said, let's take a look at our device and see how things are how's that? Yeah, and finally, this is where the output is. This is V out. Okay, all right. So use the eraser here. Try to erase some of the stuff that we unnecessarily here. Okay. All right. Okay. Cool. All right. Now let's assume in the beginning, okay, we are going to take a look at when the input is. So you can see here there are 3 cases. Case number 1, case number 2. Oops, that's not what I want to do. Okay, let's get our pen here back. Okay, and let's have what color? Okay, so we have 3 cases for the input. Case number 1, case number 2, and case number 3. In case number 1, when the input is less than VBE, which is the one that turns on the device. So basically, we are the VBE for forward active. If this is less than 0.7, if the input, the case number 1, is less than 0.7 volt. Now, here he referred to this as VBE off. This is really is less than 0.7. Okay. Now, if this is the case, okay, then this means that this device is in the cut-off region, and in this case, what happens is that the RB, the current in the base that goes through the RB, which is IB, equals 0, and the current, okay, so the current that goes in here and the current that goes through the collector IC is also equals to 0, and the current through the emitter is also equals to 0. Right? Now, word of caution here, the collector is equal to 0, provided you don't have anything that drains current in the output. So, and we are assuming that there is nothing. Okay. So in this case, what's the output value of, what's the voltage on the output? On the output, this node here. Okay. Well, very simple. The output voltage in this node equals 5 volt. Why? Because there is no droppage through the resistor here. The voltage through the resistor, the voltage droppage through the resistor is 0. There is no current through the resistor, therefore there is no droppage through the resistor, and therefore the voltage output equals the power supply voltage, which is 5 volt. And this case is when what? Watch the important condition, when our device is in the off state. Okay, now, and this is in what case? When the input is less than 0.7. So look at this series of events. Basically, one thing is causing another thing. So because we are controlling this device through the input, if the input is less than 0.7, therefore the transistor is in the cutoff region. Therefore, the droppage through the RC resistor in terms of voltage is 0. Therefore, the output voltage is 5 volt equal to the power supply. Okay, so that stays. Now, take a look at this here, this drawing here. You can see that here, what we are drawing here is the characteristic curve. And this is the characteristic, the transfer characteristic curve. We'll see that as long as the input less than 0.7, what's the value of the output? So this is the axis of the y is the showing the output voltage. The x-axis is showing the input voltage. As long as the input voltage is less than 0.7, the voltage of the output is equal to power supply. And notice that he's saying, he's showing that the Q is off. What is the Q? Well, it is the name of this transistor. This transistor, we will call it Q, and its value or state is cut off. Okay. All right, let's go into an interesting region. There seems to be there is no action here. Let's go to a region where is there an action. So let's erase this now, and we'll go into a region where there is some action, where we can take a look at things more interesting. But this is, we covered what? Case 1. And in case 1, we know that the input voltage is less than 0.7. By the way, some of the authors and textbook, they like to change the values of 0.7, and for me, I don't change them. 0.7 is when VPE equals 0.7, it is when the device is active. So we finished case number 1. Okay. So let's go back to our pen here. So we finished case number 1. Let's go to case number 2. So let's draw the circuit one more time. So I've got what? I've got my resistor, which is the RC, okay, and then my BJT device, right, and then my resistor, which is the RB, okay, and this is my input voltage, all right, and this is the emitter is connected to ground, and this is here the power supply. Okay, this one here is VCC equals 5 volt. Always I will use 5 volt. Okay, because this is typically the typical values for these things. Okay, so we looked at case number 1 here. Let's take a look at case number 2, where VPE equals what? So we start raising this voltage. We're going to raise this voltage slightly here. Notice this here we're going to start raising this voltage until I establish the voltage here, VBE equal 0.7. Okay, in this case, this transistor will be in forward active region. And in this state, what happens? Well, what happens, I know that IC, the current through the collector, equals beta times the current through the base. All right. But what is the current through the base? Well, the current through the base, okay, is simply the subtraction between VI and minus VP. So let's give some example numbers here so that we can run those through. Okay, let's take some example numbers. Suppose I have the current here, the input voltage, sorry, the input voltage here is 0.75 volt. Okay, so what's the current here? What's the value of the IB? The value of the IB equals, okay, 0.75 volt, which is the volt at the input, minus 0.75 minus 0.7, which is the VBE, okay, and divide that differential voltage by the value of the RB, the value of the resistance, okay. So the differential voltage across the resistance, okay, divide by the resistance gives me the current. And I know that IC equals what? Beta times IB. So here I found out IB, and here I found out IC. Typically, you are given beta in the question. Okay. And now the question always, what I want is to find out the output value here. Well, I know that VCC equals from Kirchhoff current voltage law, IC times RC plus V out, right? Okay, so this is from this. I'm applying Kirchhoff voltage law here. Okay, so I know what is VCC. I know the value of IC because I computed here. I know the value RC, and then from here I can find out V output. And you can see that the V output diminishes with the increase in IC. Okay, and that's why you can see that this region which is right here, okay, you can see that this is the region here which is right here. Okay, you can see that as we increase the input here, you can see the value of the output decreases, because as we increase the input, the IB increases, the IC increases, and if the IC increases, VO decreases, and we go all the way up to a point where I reach to this point, which is VIH. What happens in VIH? When I reach VIH, it is the point when I will establish this device and put it into saturation. Okay, and let's see how we put this device in saturation. So let's use the eraser one more time. Okay, and erase all of this and see what happens into saturation. Okay, so we are erasing this, okay, very quickly here, and so we can see what happens in saturation. Okay, and so basically you have to remember saturation occurs when VPE equals 0.8 volt. Okay, so saturation happens and occurs when VPE equals 0.8 volt. So let's go here and draw the circuit one more time. So you've got here your VCC equals 5 volt, and I have my RC and the collector, and then this emitter connected to ground, and then I have my RB, okay, and it's connected to the input voltage. Okay, now this is the output voltage here. What happens in saturation? I will raise the input up to a point where I establish successfully a voltage of 0.8 volt. All right, so what, and this in this case, when VBE equals 0.8 volt, okay, equals 0.8 volt, then this transistor is now placed in the saturation region, where I know that the differential voltage between the collector and the emitter equals 0.2 volt, and this is referred to as VCE saturations. VCE, VCE saturation, I will always assume it is 0.2 volt. Okay, unless I tell you in the exam otherwise, which typically I don't. It is always a VCE saturation 0.2 volt. Now, in this case, what happens? Well, what happens now? A VO is 0.2 volt, and as you can see in this region here. Okay, you can see here this is equals to 0.2. Now, so oops, we got messed up here a little bit. Okay, so now, so the question, what is the value here? What is the value of VIH? This one here. Okay. Well, the value of the VIH, really, it is the voltage when I establish this 0.8 volt. So you have to think of it as you have the VI equals IB RB plus 0.8 volt, which is the VPE in saturation. Okay, and we can compute this given the values of the resistor and other parameters in the circuit. Okay, so eventually I'm going to get something, this curve, which is, this is the transfer characteristic curve of this curve, which is the transfer characteristic of an inverter. When my input is low, my output is high. When my input is high, my output is low, and there is a transition value here. Okay, one thing to mention here is that of course, here I can calculate here the value IB if I give you the input. So the IB, I can find it out. And the IC equals some beta times IB. Okay, but I have to have a diminishing factor here. Okay, so because of it's it is in saturation. But better yet, to be more accurate, especially when you go into the saturation region, a more accurate way to compute it, it will be especially the IC current, it will be the following. Okay, or the correct way to since you have here an IC current, right, and I have this is at 0.2, so IC equals times RC plus 0.2 volt equals 5 volt. I know this value. I know the RC. I know 0.2. I can find out the IC. Okay, this is how you find out the value of the IC, right, at the saturation region. Okay, so this is the circuit analysis of the resistor transistor logic inverter, and I have gone a little bit deep or more deep than what I will do in the other circuits, because we want to understand how we analyze these circuits and how we find the currencies the currencies and voltages of the circuit. Okay, so please be in the quizzes and the exam, these values of the RB and the RC will be populated with values, and I'm gonna give you an input value, and you have to determine the saturation region, the forward active region, the cutoff region, and find out the output. So be prepared for such questions. Okay, so this is here the inverter, right? Now let's to go back to our slides, and what we can do here is that we can extrapolate the inverter and say, hey, we can build other circuits, which is I can build a NAND gate by stacking two transistors as such. Okay, and I can build a NOR gate by connecting those transistors in a parallel way. Okay, and in this stack, by the way, we will connect the output to a low value if this is a high and if this is a high voltage. And on the NOR gate, okay, on the NOR gate, if any of those is high, then I'm going to connect this to a low voltage. This meaning the output. If any of the inputs has a high voltage, the value of the output will be low, which is the NOR gate. Okay. And this concludes my lecture on RTL, and I'm gonna go to the next circuits in other lectures, and thank you very much.